Hi everybody, it's Sunday, April 6th, and here we have the solutions of the exam review questions. First question, let's see, the histogram shows the burnout time for 45 randomly selected light bulbs. The claim is that the population mean burnout time is 700 hours. The objective is to see whether the data supports this claim. Let's have a look. So we can see the distribution for individual burnout times is heavily skewed to the right, as it says in the scenario description. We have Minitab output of all kinds. We can see what the hypotheses are for the test. We can see that it's a two-tailed test. The parameter of interest is the population mean burnout time. So the first question is to calculate a 95% confidence interval for the population mean burnout time and also the test statistic, the t statistic. So in order to calculate the confidence interval, we need to know what the critical value will be for a 95% test. The sample size, which I already forget what it was it 45? Let me go back. The sample size, yeah, n is equal to 45. So that means the degrees of freedom for this critical value is 44. And so the best we can do from our table is to estimate the critical value by looking at 40 degrees of freedom. We're looking for a 95% interval, and so the critical value, 2.021. So now calculating our confidence interval. As always, confidence intervals have the same form. We have a point estimate for the parameter of interest plus or minus a critical value times a measure of uncertainty. So here we actually get, let's see, the point estimate is the mean value, which is from the Minitab output. The critical value is 2.021. And the standard error of the mean is actually given. So there's no need to calculate it. Now, if you were to calculate the standard error for y bar, you would take the 523.6 divided by the square root of the sample size, 45, and you would get 78.1. But here, because they give us the standard error of the mean, we don't need to bother with that calculation. We just plug that in. We multiply the critical value with the measure of uncertainty, and then we add and subtract to get the bounds of our interval. And we can see that those bounds are a good match with the Minitab output. Minor differences there due to differences in rounding. Calculating the test statistic. The t-statistic has, again, just like a confidence interval, the t-statistic has this common form that we see over and over again. It's going to be the point estimate that we get from the data minus the parameter of interest as it is assumed to be in the null hypothesis and divided by a measure of uncertainty. And so in this case, we're comparing the sample mean is 600.7 minus the hypothesized mean that we would expect to see on average if the null was true, and divided by the measure of uncertainty, we get minus 1.27, which is in agreement with the Minitab output. So next, does the data support the claim? We're going to answer in two ways. One way is going to be to interpret the confidence interval, and the other way is going to be to look at the p-value and comment on the strength and significance of the test. So looking at that interval, assuming all conditions are satisfied, and remember, if you have to write out an interpretation of a confidence interval, just start with these words, assuming all conditions are satisfied. I will be looking for that on the final. So assuming all conditions are satisfied, we are 95% confident that the population mean burnout time is between 442.86 and 758.54 hours. Since 700 is in this interval, it is plausible that the population mean burnout time is 700 hours as was claimed. So the confidence interval provides evidence that supports the claim that the population mean burnout time is 700. All right, I'm just thinking for a minute there. So I just want to emphasize that we cannot conclude that the population mean burnout time is 700 because the population mean burnout time could be anything in this interval, plausibly. But 700 is among the possible plausible values for the population mean. And so we have no reason to say it's not 700. Looking at it the other way, we can see the p-value is quite large. And so in terms of strength, the p-value of the test, because it's 0.21, there's no evidence against the null hypothesis. And since we're testing at 5%, we can say there is insufficient evidence at the 5% level of significance to reject the null hypothesis that the mean burnout time is 700 hours. Right. Again, of course, we cannot say that the mean burnout time is 700 hours. We can only say that we have no evidence to think it's not. Next question. Here we're looking at a two-sample t-test. So we have 100 randomly selected novice chess players, 50 boys and 50 girls, spent 6 weeks in chess camp. The playing strength of each student, which is a quantitative variable, was assessed at the end of the camp. The claim is that girls are inherently better at chess than boys. Both sample sizes are sufficiently large to assume that the standardized difference between sample means follows a t-distribution. In other words, I'm saying model assumptions are satisfied. The degrees of freedom is given, and of course, in the one instance of a two-sample t-test, this is the one model where we have to tell you what the degrees of freedom is, and here we're telling you it's 89. The question is, does the data support the claim that girls are better? Now, reading this, it's clear that the question posed calls for an upper-tailed hypothesis test. But for some reason, when I did the analysis in Minitab, I conducted a two-tail test. So if you read this and thought this must be an upper-tail test, well, you're correct. But I'm just going to go ahead as if it was a two-tail test because that's the Minitab output that I have provided. So as you can see here, I actually conducted a two-tail test, kind of by accident, but we can proceed as if that is what was asked for. So we have all the information here. Let's now look at our individual questions. So the first one is we're going to calculate a 95% confidence interval for the difference between the population mean playing strength of girls versus boys. And we're also going to look at the t-statistic for the null hypothesis that those two population means are equal to 0. In this case versus the two-tailed alternative. Right, so to calculate the confidence interval, we need a critical value. So we're given that the degrees of freedom is 89. The best we can do is to estimate the critical value using 75 degrees of freedom in our table. It's a 95% interval, so the critical value is 1.992. So plugging all that in, here we have a point estimate for the difference between the population means, plus or minus critical value times the standard error. Now we need to calculate that standard error. This, of course, is the most complicated calculation you might be asked to perform, and there's a chance you might not even be asked this on the final, but you need to be ready for it just in case. And so all the information you need is in the table. We have our sample sizes, and we have our sample standard deviations. And so plugging those into the formula, we get a standard error of 21.7351. And so now proceeding, we can look at the sample means. The difference between the sample means can be calculated. It turns out to be 21.6. Our critical value that we looked up was 1.992, and our measure of uncertainty is the standard error that we just calculated. And so multiplying first and then adding and subtracting, we get the bounds for our confidence interval. Here we have a confidence interval for the difference between the population mean responses, girls minus boys. And so you can see that is an agreement with the Minitab output. Again here, as we saw previously here, slight differences can arise in the Minitab output due to differences in rounding. So we don't need to worry too much about that. Here we're going to calculate now the test statistic. We need the standard error to do that. So our test statistic would be the difference in the sample means that we observed minus the difference we would expect to see if the null was true. And here the null hypothesis is that the population means are equal to each other, meaning their difference is 0. And we divide by that standard error. And by the way, I have labeled here standard error of y bar. That's not correct. It's the standard error of the difference between sample means. And so let me just fix that. We have our population means here as we saw before. The difference is 21.6. 21.6 minus 0. We don't really need to put the 0 there. And we're dividing by that standard error that we calculated. We get a test statistic of just about 1. And you can see that's in close agreement with the Minitab output, which gives 1.00 exactly. Okay, now we're asked, does the data support the claim? We're going to answer in two ways. One, by looking at the confidence interval, and two, by looking at the p-value for our test. So here's our confidence interval. We can say, assuming all conditions are satisfied, we are 95% confident that the difference between the population mean chest playing strength for girls minus that for boys is between our two bounds. Since 0 is in this interval, it is a plausible value for the difference in the population mean chest playing strength for girls minus boys, and we therefore cannot say that girls are better than boys on average. Looking at the test statistic, take that back, we did calculate the test statistic. Looking at the strength and significance, we just need to check out that p-value and compare that with the level of significance. So first of all, for strength, the p-value of the test is 0.32, and so there's no evidence against the null hypothesis. It's a very large p-value. For significance, there is insufficient evidence to reject the null hypothesis that the population mean chest playing strength for girls is the same as that for boys, testing at the 5% level of significance. Okay, moving on to the paired t-test. Here we imagine that a clinic randomly selected 15 patients with asthma and measured their lung volume, which is measured in liters. That's a quantitative measure. They measured their lung volume before and after taking the medication. So the claim is that the medication increases lung volume. The objective is to determine whether the data supports this claim. Although the sample size is small, it's only 15 patients, we can assume that the standardized mean difference in lung volume follows a t-distribution with 14 degrees of freedom because lung volume is known to be approximately normal in distribution. In other words, I'm justifying the claim that model assumptions are satisfied. And so we can go ahead and do calculate a t-statistic and conduct our test. The main reason why I said that in this scenario is some people might have looked at 15 and said, wait a minute, that's kind of small. Do we need to be concerned? Well, I'm telling you we don't. So we're all good. Conditions are satisfied. So here's all the data. You can see that it is an upper tail test where we're looking for evidence that taking the medication resulted in an increase in lung volume. So that makes it an upper tail test. So let's look at the individual questions. First, we're going to calculate a 95% confidence interval for the population mean. Well, why does it say population mean burnout time? That is silly. So if you bear with me for a moment, let me just quickly correct that. How embarrassing is that? Let's see. So I have to look for, if I can find it quickly. Review questions for final exam. You know how many times I reviewed these slides to check for errors, and I didn't even notice that one. What's taking this so long? Hello? Not responding? Let me try once more. Let's see. Here it is. Yeah, I'm not going to edit this out because it's good for you to see that I make mistakes too. We all make mistakes, and that's okay. Let's see. Here it is. So this is the answer, or sorry, the question rather that I want. So I'll take that, plug it in here. Nope. There. Let's see, like that. Yeah. Okay, let's see if this makes sense. So here we're going to calculate the 95% confidence interval for the population mean change in lung volume. Yes, that's it. And the t-statistic, the test statistic as well. So in order to calculate the confidence interval, once again, we need to get a critical value for that interval. For a 95% interval, the degrees of freedom would be 14 because the sample size was 15. So we actually have 14 degrees of freedom on the table. Our critical value is 2.145. So going on now to do that calculation, we're going to compare, well, we're going to take what was observed. So this is the mean difference after minus before. plus or minus the critical value multiplied by our measure of uncertainty. So all of the information that's required is in this table. We have our mean and we have our standard error already given to us. And so we just take the sample mean plus or minus critical value times the standard error for the mean. So we multiply first and then we add and subtract. And you can see that this interval is in agreement with the Minitab output. So here, continuing with the calculation of the test statistic. So here again, test statistic, we look at what was observed minus what we would expect to see if the null was true. In this case, that is 0. And we divide by our measure of uncertainty. So we have our mean, we have our standard error. We can just divide that out, and we get 2.94, which is in agreement with the Minitab outputs. So now we're going to draw conclusions, starting with the confidence interval. So here, assuming all conditions are satisfied, we are 95% confident that the population mean difference in lung volume, that's after minus before, is between 0.40 and 2.26 liters. Since 0 is not in the interval, and the interval is positive, we can conclude that the population mean change in lung volume after taking the medication is greater than 0, and that the medication is therefore effective in increasing the lung volume. All right, so I think I just want to emphasize that in answers like this one, and you might have noticed in the other interpretations of confidence intervals, I'm taking care to make sure I'm giving the interpretation in the context of the scenario, right? So that's something to be aware of when you're interpreting confidence intervals on the final exam. In terms of strength and significance, we're testing at, we're testing at 5%. So here the strength is, the p-value of the test is 0.005. And so looking at our table with adjectives, we can see there's strong evidence against the null hypothesis in this case. And then the significance, we can reject the null hypothesis at the 5% level of significance and conclude that the population mean change in lung volume after taking the medication is greater than 0. In other words, the medication is effective in increasing lung volume on average. Good. Let's see what else. Okay. Oh, next, now we're moving on to a chi-square test. This is the goodness of fit test. So here, past data collected by the former CEO of a large company indicates that 15% of the population of employees drink 2 cups of coffee per week, 13% 1 cup per week, 27% 1 cup per day, 45% 2 or more cups per day. The new CEO, who introduced the morning exercise activity, wanted to see whether the exercises have changed the coffee consumption distribution based on a survey of 400 randomly selected employees. Okay, so here's the data. So we have one categorical variable with 4 categories in total. We have our observed values. We have what we would expect to see if the null was true based on those test proportions, and we have the contributions to the chi-squared. So the first question here is calculate the chi-squared statistic and compare the value you get to the critical value for a 5% test. Right, so calculating the chi-squared statistic, we just need to add up these numbers. These are the individual contributions. So we'll do that in a moment. Here it is. Adding those together, we see our test statistic, our chi-squared test statistic is 16.64. How many degrees of freedom do we have? In the case of a goodness of fit test, the degrees of freedom is the number of categories. We have one categorical variable with 4 categories. It's that number of categories minus 1. And so the degrees of freedom is 3. We're conducting a, was it a 1%? No, it was a 5% test. And so the critical value is 7.815. So we can see then that our critical value, our test statistic is bigger than the critical value. So we're going to reject the null at the 5% level of significance. So here, in this answer that I wrote here, I'm pointing out the null hypothesis just to remind you. The null hypothesis is that the morning exercise activity did not change the coffee consumption distribution for the population of employees. Since the test statistic is greater than the critical value for a 5% test, we can reject the null and conclude that the population coffee consumption distribution has changed since the introduction of morning exercise activity. Okay. Here we're going to show how an expectation and a contribution is calculated here for 1 cup per week. So the expected value would be the test proportion multiplied by the total sample size, which was 400. So we get 52, and you can see that's in agreement with the expectation given in the table. And the contribution to the chi-squared statistic, well, that's always the observed minus the expected squared, divided again by the expected. We get 9.30769, which is in agreement with what we see in the table. And then here I'm asking one extra question. Given the large size of this contribution, does the data suggest that the proportion of employees in the population who drink 1 cup of coffee per day changed? And if so, did it go up or down? Right. So you can see that the deviance for this category, it's negative, right? It's minus 22. So what that means is what we observed is less than what we would expect to see on average if the null was true. It's quite a bit less. It's 22 people less, given a sample size of 400. So this also gives rise to a contribution to the chi-squared statistic that is very large. And so what does this suggest? It suggests that there has been a significant reduction in the population proportion of employees who drink 1 cup of coffee per week since the introduction of the morning exercise activity. So this is just an illustration of the kind of additional inferences you can make by looking at the analysis, looking at the resulting chi-squared contributions. Next one. Moving on to the homogeneity test. Here, University of Sports Ball in Canada consists of 3 divisions. This is actually something we actually did during one of the lectures. Here we're going to construe each of the 3 divisions of sports ball players as a population. So we have 3 populations, and it is known that some players use steroids, but it's not known whether the proportion who do so is the same for all 3 divisions. And so we're going to take a random sample from each of these 3 populations, each of these 3 divisions, and we're going to ask whether the distribution, yes, across the 2 responses, yes and no, whether that distribution is the same for all 3 populations. So that's a homogeneity test. So here's our data. We're going to calculate the chi-squared test statistic and compare it with a critical value for 1% test. So before we do that, we need to determine the critical value, and in order to do that, we need the degrees of freedom. So looking at the table, you see that we have 3 rows and 2 columns. So the degrees of freedom is the number of rows minus 1 multiplied by the number of columns minus 1. In this case, you get 2 degrees of freedom. For a 1% test, that gives us a critical value of 9.21. Now, to get the test statistic, we just have to add together these 6 individual contributions. And doing so, you get a number 1.34005. And so what can we conclude? What can we conclude by this comparison of the test statistic with the critical value? We can conclude that the null hypothesis, the null hypothesis is that the population distribution is the same for all 3 divisions. Since the chi-squared test statistic is less than the critical value for a 1% test, we fail to reject the null hypothesis at 1%. Next question is to show how the expected count in the contribution to the chi-squared statistic was calculated for the for the response yes in division 2. So we're looking at this contingency. The expected value when you're working with a contingency table is going to be the column total divided by the grand total times the row total. So here the column total is 25, the grand total is 1939, the row total is 436. We get an expectation of 5.62, which you can see is in agreement with what's in the table. The contribution to the chi-squared statistic, as always, it's what you observed minus what you would have expected to see if the null was true. Square that value and then divide again by the expectation. We get 1.00790, which is in agreement with what's in the table. They're just minor differences due to rounding, differences in rounding. So we're good. Independence test. Here in a survey that included 434 randomly selected participants drawn from the Canadian population, people were asked to report on their smoking habits and their heart health. The objective was to determine whether there is an association, or in other words, a dependency between smoking and adverse health outcomes. So again, we're going to start by comparing our test statistic with a critical value. And so to do that, we need to find the critical value. And to do that, we need to know the degrees of freedom. So here too, we have a table with 3 rows and 2 columns. So the degrees of freedom again is 2. In this case, it's a 5% test, so the critical value is 5.991. In order to calculate the test statistic, we need to add up all of those individual contributions, and doing so gives us our chi-squared test statistic, 21.3592. As you can see, what can we conclude? Well, the null hypothesis is that there is no association between the 2 categorical variables. Since the chi-squared test statistic is greater than the critical value for a 5% test, we can reject the null hypothesis and conclude that there is an association between smoking intensity and heart disease. Next, we're just going to do a quick calculation. Actually, we're going to do 2 calculations. We're going to calculate the expected count and the chi-squared contribution for both healthy and heart disease given non-smoker. So starting with healthy, here's our contingency. The expected value is the column total divided by the grand total times the row total. So that gives us an expected count of 189.31, which is in agreement with the Minitab output. The contribution to the chi-squared statistic is what we observed minus what we would expect to see if the null was true. Square that value, divide again by expectation, we get 0.0719. Again, in agreement with the Minitab output. So good there. But we're also asked to calculate the same for the heart disease category. So moving on to that. Here again, we're looking at the column total divided by grand total times the row total. This gives us the expected counts if the null was true. 18.69 in agreement with the Minitab outputs. And the contribution to the chi-squared statistic observed minus expected squared, divided again by expectation, 0.7285 in good agreement with the Minitab output. So we're good there as well. Moving on to one-way ANOVA. Here we're imagining a pharmaceutical company invented a new drug for a common illness. As the last phase of research, they needed to determine the optimal dose, and so to do so, they randomly assigned 50 volunteers with the illness to each of 4 groups. The groups received a placebo, 1 dose of medication, 2 doses, and 3 doses. Respectively, a quantitative measure was then taken to assess the efficacy of the treatment for each individual, higher values indicating a greater reduction in the symptoms of the illness. So in other words, higher values mean the medication or the dosage was more effective. So first question, what is the null hypothesis for the test? Well, the null hypothesis is that the population mean response is the same for all 4 dosage levels. If we fail to reject the null, then we can only conclude that the evidence suggests that the medication has no effect. Show how the test statistic was calculated and provide an appropriate conclusion for the omnibus test based on the p-value. So the test statistic is a ratio of variances. We look at the variance attributed to the factor, which in this case would be the dosage level, and we divide that by the variance attributed to individual differences between individual test subjects. And so that ratio gives us 47.6423 in agreement with what we see in the Minitab output. Now the p-value for that test statistic, which by the way is that F statistic is very large, no surprise, the p-value is 0.000. So here the strength, the p-value of the test is 0.000. So there's very strong evidence against the null hypothesis. And for significance, we can reject the null hypothesis at the 5% level of significance and conclude that at least one population mean response is different from the others. Right, so I just want to emphasize again, for analysis of variance, the omnibus test It's just testing whether the population mean responses are all the same. And if we reject the null, then we can conclude that at least one population mean response is different. That's the omnibus test. Once we reject the omnibus test, of course, now we have to look at where the differences are, and for that we do the multiple comparisons. Oh, for some reason I'm putting a box around that. Let's see. So looking at the multiple comparisons, before we talk about those, let me just remind you of how you could determine the number of comparisons that are necessary given the number of factor levels. So in this scenario, we have 4 factor levels. And so the number of comparisons is 4 times 4 minus 1 divided by 2 gives 6. Now, for those of you who weren't in class on Thursday, we did talk about this method for calculating the number of comparisons. This is something that was also covered in the lab. The reason why I didn't cover it in class is because I didn't think it's really something that's necessary for you to know. But then I looked at the final and see that there is a question on the final where you do have to do this kind of calculation. So there it is. Put this on your formula sheet so that you get that question correct. Here in this case, you can see that we get 6 comparisons, and looking on the left-hand side on this graph, we can see indeed there are 6 pairwise comparisons. So what do these comparisons tell us? Well, what we're most interested in is which dosage level provides the greatest response in terms of relieving the symptoms. So remember, initially I said higher values for our response indicate that the medication did better. So higher values mean more effective. The dosage is more effective. So keeping that in mind, looking on the left, we can see a couple things. First of all, this grouping table that you can see on the left, the individual letters indicate population means that are inferred to be unique. So in other words, dose 2, you can see, it has a unique letter. It's the only factor level that is given the letter A. That means the population mean response for dose 2 is inferred to be different than all the rest. Not only is it different, but it's also indicating that that population mean is the biggest, because you can see that the sample means are in order, and so from biggest to smallest. And so we can infer from this table that dose 2 results in the greatest population mean response. Doses 1 and 3, you can see, have the same letter, and so we can infer that the population mean response for dose 1 and 3 are the same. Statistically, they're not any different. C has its own letter, and that's the placebo, and of course that has the lowest population mean response. So you can see that from the grouping table. You can also infer the same thing, that dose 2 is the best. It provides the greatest effect. You can see that looking at the table on the right. And so in particular, if we look at the intervals that compare dose 2 with the other population means, you can see dose 2, the population mean response for dose 2, compared to placebo. Here we have a confidence interval that is positive, indicating that we can infer that the population mean response for dose 2 is bigger than that for placebo. Likewise, dose 2 compared to dose 1, we can see the population mean response for dose 2 we're inferring is greater than the population mean response for dose 1. Comparing dose 3 and 2, you can see dose 3 is now the first one. This interval is negative, indicating that the population mean response for dose 3 is less than the population mean response for dose 2. So taking these together, we can infer that the dosage that is most effective, that gives us the biggest response, here bigger is better, is dose 2. And so we can just write that. We can say for grouping information here, that's on the left, indicates that the population mean response is greatest for dose 2, the same for doses 1 and 3, and the least for the placebo. Looking at the simultaneous intervals for differences in population mean responses, we can see that dose 2 is better than the placebo because the interval is positive. Dose 2 is better than dose 1, again, because the interval is positive. And dose 3 is worse than dose 2. That interval is negative. And so there's evidence that dose 2 is the best. checking some conditions. Here we're looking at the residuals. We're going to test two conditions. We're going to test the normality assumption and the equal variance or equal spread assumption. So here, looking at normality, when you come to a question about model assumptions, if you have to write out an answer, so in some cases it might be multiple choice and you just choose an answer. If you have to write the answer out yourself, the first part of the answer that I want to see will indicate which plot you're looking at. So in some cases you might be given 2 or even 4 different plots. And you're asked, is the normality assumption satisfied? You need to first say which plot you're looking at, because if there's 4 plots, I'm not going to know. So you have to tell me. So the first part is, as I'm demonstrating here, looking at the normal probability plot. Right, so I'm indicating which plot I'm looking at. Looking at the normal probability plot, the data points are approximately in a straight line, and this indicates that the residuals are approximately normal in distribution, so the assumption is satisfied. Likewise, if you're testing for constant variance, looking at the versus fit plot, the spread of the residuals is about the same for all 4 dosage levels, so this assumption is satisfied. So don't forget, if you have to write a long answer for a question like this one where you're assessing whether a model assumption is satisfied, if the assessment involves looking at a plot, start by indicating which plot you're looking at. Right, I will be looking for that indication when I mark your final. So please make sure you say looking at the versus fit plot, or looking at the normal probability plot, or whichever plot you're looking at. Please don't forget to do that. Okay, moving on to 2A ANOVA. Oh, here, this is one of the ones we did in class, actually. So here are populations of goats living at higher altitudes adapted to use oxygen more efficiently. To find out, biologists measure the oxygen utilization efficiency of goats living at different levels of elevation. They included 2 factors: the location, sea level, highlands, and mountain, and the sex of the goat, male versus female. So here's our data. Let's see. What is the hypothesis for the omnibus test for location? I want to emphasize the next problem, which is also the last one, the last exercise, is multiple regression. For multiple regression, there's one omnibus test. That's for regression. We'll be looking at that in a moment. For 2A ANOVA, there's 2 omnibus tests, one for each factor. Of course, for one-way ANOVA, there's a single omnibus test. And so what is the omnibus test for location all about? That omnibus test is, well, the null hypothesis there is that the population mean response is the same for all 3 locations. If we reject the null, we can conclude that at least one location has a different population mean response. Likewise, for sex, that omnibus test is that the population mean response is the same for female versus male. If we reject, then we know that there's a difference. So here, what are the hypotheses for the omnibus test for location? The null hypothesis for the omnibus test for location is that the population mean oxygen utilization efficiency is the same for all 3 locations. The alternative is that the population mean is different for at least one location. So notice here I am stating both hypotheses because the question said, what are the hypotheses, plural? It's asking for both. If you're in doubt, if you're asked about hypotheses, if you're in doubt, include both the null and the alternative. Next, show how the F statistic for location was calculated. So that F statistic is a ratio of variances. We have the variance that is associated with differences in location. We compare that with the variance associated with individual differences between goats. That ratio turns out to give an answer of 43.9707. And you know what? I just noticed that that's different than the F statistic that's in the table. So probably when I wrote down this answer, I put 43 instead of 53. So let me just double check that. Just open my handy dandy calculator here. Okay, so we have the variance associated with differences in location, and we divide by the error variance, which is due to individual differences between goats. And indeed, it's 53.97. So for some reason, I put a 4 instead of a 5. And so there we go. So that is in agreement with what we see in the table. So far, so good. So that's the hypotheses. That shows how the Fisher statistic was calculated. And now we're going to talk about conclusions based on the p-value, right? So the p-value is 0.000. So we have very strong evidence. So we can say we have very strong evidence against the null hypothesis of the ANOVA test for location. And for significance, testing at the 5% level of significance, we reject the null and conclude that the population mean response is not the same for all levels of location. Right, so very important when we assess the strength, we just say, we just write down the appropriate adjective for the strength against the null hypothesis, or in favor of the alternative if you want to say it that way. But we don't draw any conclusions when we're assessing strength. We only draw conclusions when we're talking about significance, and even there, we only do so if we're given a level of significance. So that's just a reminder to make sure you make that distinction between strength and significance. Here, looking at the table, well here, since we rejected the null hypothesis, we can conclude that the population mean is different for at least one of those three locations. And here now we have a table, and we can figure out where those differences are. So looking at this table, we can see that all three intervals are positive, indicating that for every pairwise comparisons, those population means are different. So now before going on, let me just remind you again that if you were asked how many comparisons are necessary, let's say you didn't have a table to look at, and you're just asked how many multiple comparisons are there going to be. Again, it's just the number of factor levels, in this case 3, times that number minus 1 divided by 2. And so in this case, you can see that we have 3 comparisons. You can see in the table there are 3 pairwise comparisons. Now, what do we notice about these confidence intervals? None of the intervals contain 0, and all are positive. And so the population mean oxygen utilization efficiency for location 2 is greater than that for location 1. That's the first row. For location 3, it's greater than location 1. That's the second row. And for location 3 is also greater than location 2. That's the third row. So putting these together, what does that tell you? That tells you that the oxygen utilization efficiency is greatest for location 3. Is this the last question? I think it might be. Let's see. Oh, right. I almost forgot. We have a multiple regression. Okay, let's finish with that. So here, this again is an example that we covered in class. So is the life expectancy for a U.S. state associated with quantitative variables such as the proportion of adults who are high school graduates, the proportion of adults who are illiterate, or the mean household income? To find out, we got a bunch of data, and here is our table. So first, what are the hypotheses for the omnibus test? So the first row, the one that says regression, that is the row for the omnibus test. The null hypothesis of the omnibus test is that the population slopes for all 3 predictors are 0, meaning that there is no linear association between the response and any of the predictors. The alternative is that at least one population response is one population slope is non-zero. Showing how the F statistic is calculated, again, it's a ratio of variances. We look at the variance attributed or explained by the regression model and divide by the variance attributed to individual differences between these 48 states. That ratio gives a very large number, 19.8328. And you can see the associated p-value is very small. So now we can comment on the strength and significance of the omnibus test. Looking at that p-value, we have very strong evidence against the null hypothesis of the omnibus test, so the p-value is very small. And for significance, testing at the 5% level of significance, we reject the null and conclude that at least one population slope is non-zero. Testing at 5%, if we look at the individual tests for income, high school grad, and illiteracy, it's only illiteracy that for which we reject the null at the 5% level of significance, as you can see. Next, we're going to calculate the 95% confidence interval for the population slope associated with illiteracy. And then we can check our answer by looking at this table. Now, before we do that, we need to know the degrees of freedom because, of course, for a confidence interval, we're going to need a critical value from a t-table. To get that, we need the degrees of freedom. So I'll remind you that for multiple linear regression, the degrees of freedom for our test statistic is the sample size minus the number of model coefficients. You can see from the table we have 4 model coefficients. We have an intercept, or constant, and we have 3 slopes. So that's 4 in total. So the degrees of freedom here is 48. And I just want to point out, too, that if you look at the analysis of variance table, you will notice that the degrees of freedom for the error term is also 44. Did I say 48? I meant to say 44. So the degrees of freedom is 44, and you can see that's the same as the error degrees of freedom, and that's always going to be the case. So now there's 2 ways you can figure out the necessary degrees of freedom. So now we need to approximate the critical value for the 95% interval. We have 44 degrees of freedom, so the best we can do is approximate using 40 degrees of freedom, and it's 95% interval. The critical value is 2.021. So we take our point estimate. I'm going to call it B3. It's the third model coefficient, the third slope. The fourth model coefficient, but the third slope. Right? Remember the constant, that model coefficient we call B0. For high school grad, B1, income, B2, illiteracy, B3. So that's the point estimate, plus or minus critical value times a measure of uncertainty. And notice the point estimate and the measure of uncertainty are given right there in the table. And so all we have to do is plug those numbers in bringing in that critical value. We multiply, and then we add and subtract to get the bounds of the interval. And check it out, very, very close to the Minitab output. Just a little bit different because of differences in rounding. So let's interpret this interval. Now that here it's a little bit more involved. Interpretation is a bit more involved because we're interpreting a model coefficient, which is, a population coefficient, which is a slope. So what do we say? Again, we always have to start by saying, assuming all the necessary conditions are satisfied. Make sure you include that in your interpretations. We're 95% confident that the population slope for illiteracy is between these 2 bounds. And that is, we are 95% confident that for every 1% increase in the percent of adults who are illiterate, the life expectancy will be reduced by between 0.61 and 0.178 years on average, after accounting for high school grad and income. Don't forget to include this last part. This is something that's you see in multiple linear regression that you don't see anywhere else. Is we have to just include this extra few words. Now, exactly why you have to include those, I didn't really try to explain that very clearly. You just need to remember to do so. The reasons why for many things in statistics you will learn if you take another course, let's say a course that's just all about regression. So if you're curious, I encourage you to do so. Here I was just going to change the font for emphasis. There. Right, okay, so moving on. The last thing was, what does the estimate of the population slope itself for literacy, right? So if we go back for a second, so this interval, of course, that's an interval estimate for the population slope associated with literacy, and this interpretation is an interpretation of the interval estimate. You might also be asked to interpret the point estimate, which is the individual model coefficient, which is right there. And so here you might say something like, the estimate of the population slope indicates that for every 1% increase in the percent of adults who are illiterate, the population mean life expectancy will decrease by 1.192 years on average after accounting for high school grad and income. Yeah, there we go. Yeah, and you know what? Probably you want to add this in as well, just to be sure. Let's add that in there. I don't see why I wouldn't do that. Let me turn this back to Calibri. Okay, so assuming all the necessary conditions are satisfied, the estimate of the population slope indicates, yes, that for every 1% increase in the percent of adults who are illiterate, the population mean life expectancy will decrease by 1.192 years on average, after accounting for the other two predictors in the model. So let's emphasize that one as well. There. So I think that is the last slide. Yes, this is the last slide. Let me go back. Great. Okay, now just a couple things to emphasize. These questions don't cover everything you need to know, right? They cover quite a bit of it, and they provide some practice for all the models. Apart from simple linear regression, I did not include simple linear regression here because I think most of the concepts you need are also included in multiple linear regression. An example of something we didn't see in this review material, confidence interval versus prediction interval. Right, so check that out. Make sure you understand the difference between those two things. Also, many of the model assumptions I didn't cover. So you still have your work cut out for you. But if you did complete this review material, and of course, if you're hearing my voice, you've watched the solution video, then that gives you a lot of preparation. But again, it's not everything. So be sure to look at some of the skill checks. If there's any particular topic that you are a little bit unsure of, you can go back and look at that skill check again. You can also check out the lecture slides and so on. If you have any questions about anything, send me an email. I will try to respond quickly. I'm going to check my emails quite frequently in the next several days, leading up to the final. And we also, if some of you need some face-to-face, we can meet and collaborate, and we can discuss if necessary. Otherwise, I can just send you an email response. Yeah, so I'm here if you need any help. Otherwise, I'll see you at the exam. So study well, and I'll see you there. Bye-bye.